Drepper from Red Hat, and he will be talking about processor architectures and why we should care about it.
Okay, so we have flip it to the other side. So we have a few problems with microphones here. It's not working well.
Hello.
All right, well, I have to do it like this. So I try to get the other mic to work because feel free to interrupt me at any point in time. So this will be a succession of different things I want to talk about, different types of architecture and so on. So if you wait until the end to ask your question about something specific, you might have forgotten about this or no one cares anymore. So this is more or less something like a fireside chat. So I'm going to talk about and ramble on about all kinds of architectures, the implications of that on the software itself. So whether you care or not is something which only you can decide. So if you're only interested in using your computer for something which doesn't really require much CPU cycles and so on, you probably don't care at all about CPU architecture underneath, so it just works, and perhaps a tablet or something like this is sufficient for you. So I assume that people here are therefore interested in something as a continuation of what Larry and Joe talked this morning about, so how you actually performance tune things and so on. And I will give you here the information about what is underlying this. Why are we having these kind of problems with the kernels? Why do you need these tuning parameters? And actually also scare you a little bit more, because what Larry touched on and Joe touched on in their talk, this is just scratching the surface. So they talk about some of the aspects on what you can tune. We have problems on hand which we cannot even tune into the existing kernel parameters, or don't even have the information to get the information out of the system to actually make good decisions about this. So it's really, really problematic. All right. So why is this actually much more important now than it was just a couple of years ago? And the reason for that is to some extent that high-performance computing went mainstream again. So in the very early days of computers, of course, everything was high-performance computing because no one, except for those who are doing number crunching, actually had a computer to do anything on. But nowadays, we have a new topic in place which everyone is excited about, and it's machine learning. And we have all kinds of support hardware for these kind of things. So my new phone, for instance, has support in it, in addition to the normal processor, in the processor itself, to do acceleration for just machine learning stuff. So prevalent is this kind of stuff. But machine learning and also many other topics, so just in general analytics, so statistics and so on, and also rule-based monitoring and scheduling and these kind of things, they are very compute intensive. So for those purposes, all of a sudden, people actually care about performance again of high performance of compute jobs. And the answer which especially the big CPU manufacturers have come up with looks like this. Anyone knows what it is? Too small? Well, no. Well, the cognizant expert will know it right away. So that's a Skylake core. Of course. That's basically how it looks like. And this is just, of course, at the very, very high level. The Skylake cores and similar processor cores nowadays are extremely complicated. So, and we're not going to talk too much about the individual details here. So if you want to have that known at some point at a different conference and so on, maybe you want to let me know so I can talk to you at arbitrary levels about how this kind of thing works, how it has to be programmed, how the scheduling has to work. But here we are focusing on some of the higher level aspects of the whole thing. But you should realize that, as I said, this is just a core. A processor is made up of even more than that. It has something called an uncore part, which handles the last level cache and all kinds of other stuff. So this just means a processor is incredibly complicated nowadays. And it's designed this way for one reason only, and it is it is good enough for most purposes. So this doesn't mean this is the perfect architecture to do any compute on. This is just as good as they can produce it to fulfill most people's needs, which in general, this is a sentiment of which I'm actually in favor of. So I like to think about the task of an operating system designer and so on also as providing a service which is equally bad for everyone, as opposed to good for a specific person. And the processes are just like that as well. So this does not mean, as I said, that this is the perfect architecture, and I want to show a couple of things. So the first thing is, of course, to get any kind of performance in today's processors, you need caches. So I highlighted them here. Without caches, processors would not be really much faster than those which we had in the early 80s. Simply because the memory interface is so slow. It hasn't really gotten that much faster. In theory, we can drive some of them, some little memory a little bit faster, but, well, if you nowadays want to have a machine which you want to have more than 16 gigabytes, well, you cannot drive it as fast, and you have to really slow down, etc. and so on. And to get any kind of performance out of this, you need caches. So, well, why don't we have all the memory which is available in the system in the form of caches? Well, no. Well, one question was simply that it's not physically possible because of speed of light. That's actually not possible. Just look at the the size of the DRAM chips. The structures are actually not that large by itself. So the main answer for that is simply energy. So there's a big difference between the main memory and the memory which is used for caches. So any EEs here? So what's the difference? Well, and what's the difference? What's behind these terms, dynamic and static? The number of transistors per bytes, yes, but why? Well, the one is an active circuit, the one is a passive circuit. So the DRAM itself is nothing but a capacitor, which is charged once and ideally holds its charge forever. It's not the case because of the structures, but a dynamic circuit is nothing but cross-connected, basically inverters. And that's an active circuit. It draws electricity. It's very fast because of that, because it doesn't have the discharge curves of a capacitor to deal with when it comes to performance. But it also means it needs electricity to actually function at any point in time, otherwise it loses its information. So the result is that if we would build up a system exclusively from SRAM, as it's called, static RAM, in that case, well, probably, and we try to shrink it as much as possible, probably every Intel has to deliver, in addition to the processor, a little cooling thing next to it, so which is, well, the size of a fridge, because it's tremendously hot. It's simply physically impossible. And even if we scale it down to the last level cache, which is not a level 1 cache, which is the fastest. So you can have static RAM in different sizes and different speeds and so on. So it's just a matter of how large the structures you're building and a couple of other physical aspects which determine how quickly it reacts. So the level 1 cache is different in its implementation than the level 2 cache, and level 2 is different from the level 3 cache. So they're all physically different, and the slower it is, the less energy it takes. But even the level 3 cache implementation, which is an SRAM implementation, is far more energy consuming than the DDR, so the normal dynamic memory which you have as a main memory in the system. Therefore, we actually are not going to get any faster. We are already hitting the energy boundary, and we will talk a little bit more about all the kind of energy consumptions in the CPU. Even without increasing the cache sizes too much. So in addition, and this is to some extent where things are coming on, so it becomes increasingly more problematic to actually route it on the die. And large dies have low yields at the processor manufacturing side, and therefore they get expensive to buy and so on. So every single time the CPU manufacturers are coming up with a new with the new architecture, you will see them first saying, here's the new architecture. And then they haven't yet decided how you actually will see it, how many cores, how much RAM, etc. So they're looking at the manufacturing process, decide what is the most profitable way of actually producing this, and at the same time, this means that, well, what can they sell at the top bin, at the highest speed, with the largest cache sizes, the largest number of cores. At the same time, they have to see if one of the pieces, so some part of the memory, some parts of the cores is problematic, they will have fuses built in so that they can sell a 12-core system suddenly as an 8-core system, where it's the 8-core CPU, because they just turn off 4 cores and sell it with the junk to you at a lower price. So these kind of things is all part of the equation which makes up designing a CPU. And certainly they try to increase the sizes of the caches as much as possible, but there's a really, really hard limit. Even with decreasing node sizes, so we're down to nowadays 14 nanometers on the Intel side. We're having the first 10 nanometer chips coming out. And even at those, we are at least initially not seeing any significant increase in the cache sizes. And most likely, we will never see them again. Because one of the things which is coming along, and I'm going to talk more about this also in the later slide, when I give a little bit more insight into the memory system, is that we will see, in addition to DRAM, which we see now as the main memory there, a second type of RAM available. So you can already buy this in some extensions. So most of the time you will not find it, but you can buy nowadays things which look like a DRAM module. So everyone has seen these little PCBs which have all these chips on it with RAM. Well, things like that look something which looks exactly the same, but they are not using DRAM, they're using flash. Using flash on it. So flash again has the property, unlike DRAM and SRAM, that it actually holds its information almost indefinitely. It doesn't require any kind of electrical charge to keep up. So SRAM is an active circuit, as I said. DRAM is something which requires a refresh every once in a while. So it, as I said, it has a capacitor in it, and ideally in an ideal world, the capacitor would keep it charged all the time. But in practice, this is not possible, because the structures, the fine structures of the silicon metal and method there are basically so that they are leaking, and therefore they have to be refreshed. So that is all done by the system, but it requires that the bit is read out and written back, and this requires energy. Flash, on the other hand, doesn't require that. So so flash is just one of the non-volatile RAMs. There are other ones with a PCM, phase change memory, or etc., which exist there as well. So I'm using NVRAM for all of these techniques together. So the property of that is simply that once written to, they can be read many, many times, and you always get the same information back without any active keeping up. Yes? Would room temperature semiconductors solve that problem? I don't think any of that is necessary, not with this kind of CPU design. So the charge loss and things like that have absolutely nothing to do with superconductivity. No, I meant the cache heat. With the cache heat issue, I cannot recall to have seen that we can actually produce in any amount of quantity with superconducting material these kind of capacitor which we need. You have to realize that the structures nowadays to make up the T cell for a DRAM cell are at the level of that we have something like 20 atoms involved. So I'm not sure we can actually do these kind of things with these specially doped materials which are necessary for superconductance. But perhaps in future, well, if we have absolute loss. But the problem is that the distances are so small that it's not just that we have resistance as a problem. It's simply the probability. So it's just quantum mechanic, where you have tunnels all of a sudden appearing outside to move the charge out of the capacitor. You cannot prevent that. That's pure math. So it will never go away completely, but perhaps we can do something. But it will be a computer which you cannot buy probably. Probably all of Europe could not buy one. So anyway, so I was at the NVRAM stuff. So NVRAM has a benefit that we don't have to at all spend any energy maintaining the state of it. So the idea now is to not only have DRAM attached to the outside of the CPU, so the memory controllers of the CPU are driving nowadays the DRAM modules, but also using the same interface have NVRAM in there. With the benefit, so after we adjusted the appropriate memory protocols for the DDR, etc., with the benefit that, first of all, we don't have to have as much energy necessary to keep the charge, which means that we can increase the capacity. So nowadays we have, what's the largest, 16 gig or 32 gig sticks, something like that in the order of magnitude we can put on a single stick nowadays and put in the system. 128 gigs for the largest ones, but the common ones are 16 or something like this probably, right? But it doesn't matter. So it's in this order. So it's increasing, it's going up and so on. But you can already today buy these NVRAM sticks with 1 terabyte on it. It's easy doable. So everyone has probably some USB stick with these tiny little things in there. And I have one which has 512 gigabyte there, which I bought at some point. So it's easy enough. You can do that. It's not a big issue. So it's one single chip, 512 gigabytes. So we can easily put a terabyte or more on these kind of things. So the benefit of that will be that we have addressable address space from inside the CPU without any translation. So currently you can think about, for instance, the capacity of a hard drive as an address space extension. A very ugly one in most cases, but to some extent you can map the content of a file or a disk into an address space and so on. But with this, it will not be necessary anymore. We have a flat address space which encompasses 4, 5, 8 terabytes of distinguishable and directly accessible memory locations. That's a change. It's a game changer. But the difference will be, of course, that while we already complained that DDR, so the normal dynamic memory, is slow when we are trying to access it, the NVRAM part will be yet another order of magnitude or 2 slower than that. So think about what Larry and Joe talked to you this morning about NUMA tuning and why this is so important. Well, guess what? It only gets worse. Yes?
There is also the problem of aging, because NVRAM can write
Yes, so the question was, or the comment was, sorry, there's also the problem of aging. You're right to some extent, and for Flash this is particularly bad, but Flash is just the technology we are using right now to some extent. So there are other technologies like PCM, phase change memory, which don't have the aging issues. So, and also the stuff Micron has together with Intel and so on, so they don't have the same one. They have a lifetime which is 1,000 times higher than what Flash has, something like this. And by the time this one would wear out for general production use and so on, well, you probably don't like your machine anymore and you bought it, a new one. So it's I ignore that problem deliberately. It's not really that much of an issue. But the problem is really that it's slow. It's really, really slow. So Flash is really slow. Phase change memory and so on are faster. They are working on that, but that's still an order of magnitude slower than what DRAM is. And all of a sudden, well, someone had to do the translation there. So that's Larry's work. He has to actually think about, how do I cache the NVRAM in DRAM? DRAM will not be used as memory anymore. DRAM will be a cache. Yes?
I'm not sure if you are overthinking about another problem other than the performance is because errors start to become persistent.
Okay, so the comment was about memory errors and so on. So if you have memory which survives for a long time without recharging, of course, there will be errors in there. So, but this will be mostly addressed in hardware to some extent. So you will not have necessarily even though it looks like the memory will be will be just a plain translation of the chips into addresses which you can see from the CPU itself. There will be things like error correction going on behind the scenes. So a single byte might actually be consisted in the piece, in the flash and VRAM and so on as 10 bits with error correction, one autocorrect and 2 detection or something like that. So again, something I wouldn't worry about. This will be done at the chip level. All right, so all the problems with memory and so on have led the CPU designers to come up with all kinds of workarounds, and most of them you probably know. So the good news is most of them are actually deployed and easy to use and actually require no changes to the program itself. So for instance, it's a long time ago, so 15 years ago, we started to see that the memory controllers moved from the North Bridge, which actually completely disappeared, into the CPU itself. And we don't have this bottleneck between the North Bridge and the CPU anymore. And we have multiple memory controllers now attached to a single CPU. So some of the high-end server chips have 6 or 8 or whatever memory controllers, which all can work independently of each other. So we have 8 times the bandwidth as opposed to if you have just one memory controller attached to your chip. So each of the memory controllers can have multiple DRAMs, so DRAM chips or DRAM modules attached to it. But there's a problem. If you want to have the highest speed, you only can have a single rank and one single module in it. As soon as you have dual rank, or you had a different models, the speed goes down. Because this is just pure physics. If you have multiple, this is basically one physical electric line on which you can have multiple users on it, and the more you have, the more capacitance you add, and the longer it takes for the signals to actually be clean enough to be read, and therefore the system has to be more conservative when it comes to the actual reading out of the information. So you can try to increase the memory speed, but that's then usually manifests itself in the form of an unstable system, where the information you read back, what the CPU receives back, is actually wrong. So that's what all these overclock main boards and so on allow you to do, where they allow you to set the frequency of the memory thing. Well, you can try it. If you have high quality modules and you have a good motherboard and so on, you can get a high speed. If not, well, you get failures. So the other thing which is going to come, and I have more to show for that in a similar fashion later on, a little bit more graphics, is that we are already seeing memory to move on the die, or at least in a package. So instead of having memory external to the CPU itself, it's somewhere around the CPU directly, which allows you, the CPU manufacturers, to actually access the memory with much, much higher bandwidth, because it can actually deploy many more parallel lines. So currently, for instance, DDR is a protocol which transfers 64 bits at the same time. So to transfer an entire cache line, which is the unit at which memory is accessed from the main memory, we need, therefore, 64 of these packages to be transferred, because we need 64 bytes. Oh, 8, sorry. So it's the other way around. So we need 8 of these packages to be transferred. So that takes time. So if you have on-die memory or on-package memory, we can easily get basically the required 512 bits of connectivity all in parallel, because it's so much easier for the CPU manufacturer to actually control the length and the timing and the routing of the individual lines. So that's something, but of course the size will be limited, very limited. That's not the same as cache, because it will actually be DRAM or something similar, but it's much faster and much easier to connect. So the problem with, to some extent, the way we are doing programming and so on, and the overhead associated with accessing memory, was the introduction of cache lines. So early processors didn't have that. They accessed the byte at a time, and the introduction of cache lines is simply just another optimization, because it's so much communication overhead with the DRAM modules to actually request the memory location. You better make it worth. So we are requesting 64 lines, but this means if the programmer doesn't pay attention and only uses 4 bytes out of 64 lines, well, we have an overhead. So we're using just 1/16 of the entire cache line, and everything else is wasted effort. So this is why one of the very important optimizations is simply to look at cache line utilization, making sure that you're actually using all the data without reloading, etc. So there are all kinds of things associated with that. I'm not going to the details here, so I've written some text about that a long time ago. Can read it all up. So prefetching is just another thing. This is nothing positive. You have to realize that. This is just the CPU manufacturers capitulating to the speed of the RAM. Prefetching is something which they introduced again to reduce the latencies of certain memory accesses. But prefetching never works perfectly. This is based on heuristics. So it just assumes that, well, if you have read memory location 1 and 4 and 7, well, you will probably read 10 the next, and therefore I'm trying to get this memory into the CPU caches as soon as possible before you actually use it. Well, but there's no guarantee. The CPU cannot read the program's mind when the program is mined indirectly. So prefetching by itself can be really problematic. Therefore, the CPUs nowadays have explicit prefetching in cases where the programmer can see, oh yeah, something bad is going on here, or it can actually prevent the processor from doing any automatic prefetching and so on, but that's all problematic. So it's nothing positive about that we have to do this. So the last thing I want to mention here is hyperthreading. And you might actually be confused why I mention hyperthreading in the context of memory optimizations, which they're doing. But hyperthreading has nothing whatsoever to do with parallelism at its core. Hyperthreading was purely introduced into the CPUs to hide latencies. Nothing else. So the CPU simply is using exactly the same core to execute a second hyperthread, on some systems 4 or 8 hyperthreads. So Intel's 5, for instance, had, I think, in its highest inclination 8 hyperthreads per single core and so on, because the latencies of accessing memory were so high that you might have 7 threads waiting on memory, and therefore, well, the 8th thread can actually make progress. So these kind of things are, again, they are not positive. That's yet another thing which they just added to hide, well, the inability to speed up the memory system. Yes?
Another reason for introducing hyperthreading is to visualize the increasing number of functional units available for a single core.
So the comment was there's another reason for using hyperthreads to utilize the increasing number of the functional units which exist there in the core. So what you saw at the beginning of this complicated thing. So this is true to some extent nowadays, where you can have reordering of instructions based on the hyperthread, and the retiring engines will then put them apart by itself. So, but this would only be true in unoptimized code. So, and we are not assuming unoptimized code at that point. So, which means, so you're normally reaching in optimized code, you're reaching the limit of the number of instructions which can be decoded and issued to the execution engines with one core or one thread by itself. You don't need a hyperthread for that. It's just another thing when you have code which cannot be issued in this way, which most of the time, again, happens usually because you have waiting for memory for the hundreds of cycles. Any of the operations the CPU does by itself, and leave out the division operation. But every other operation nowadays is by itself, the latency for the first word is 2 or 3 cycles. So it's not really that much. And they're pipelined. So, but the point is taken. It can take advantage of this nowadays, yes, and it's perhaps something good. And there are situations where we can exploit hyperthreads to something good. But this was marketing genius from the CPU manufacturers to sell you hyperthreads as something good. All right, so I mentioned already the memory, the problem of memory when it comes to energy use. So I've been working at some point, so I was with some organization which looked at exascale computing at some point, so there's a group which looked at these kind of things. And let's just do a little bit of math. DDR4 LP, low power DDR4, in its most optimal way of functioning, so which we will never reach, at least over a long time, requires something like 40 picojoules of energy for each bit transferred. So that's the physical limit which we have nowadays. It's in general much higher. So exascale programming means that if we have this number of 10 raised to the power of 18 operations we want to do, and operations in this case in the HPC world means double 64-bit IEEE numbers and so on, we're talking about an energy consumption for the entire memory system of such a system by itself, which by itself would be 5 gigawatts. So this is not something which we can possibly do in this form. So the current world-leading systems and so on, they really completely prioritize performance. So there's Tianhe, I think it's the one, which is the one in China and so on, which is not the energy efficient one, it's the higher performing one. I don't know how many power plants they have next to the data center over there, just to drive this one thing. And that's far from exascale. That's a petascale machine. Something like 12 or 20 petabytes or something like that. We're not even close. So something has to change when it comes to the memory architecture. We have to live with that. And this will have implication on the way we are programming things and the way we are optimizing our programs to run on that. So one way how CPU manufacturers have tried to attach this, and I mentioned this earlier a little bit, is to introduce what is called HBM, high bandwidth memory. Mostly this is today used for graphics cards, for GPUs. So I use the CPUs, GPUs interchangeably, so it doesn't matter at that point. GPUs are nothing but processors of a special kind. And we have these kind of stackable modules, which are RAM modules, which are sitting right next to the CPU core on some form of architecture. We see a couple of layers there to actually connect them. But the main point is that none of the connections between the memory and the CPU or GPU have to leave the package. And therefore, they're completely controlled by the manufacturer of the CPU. And there can be wide, there can be many in parallel, and they can be fast. So this is something which is already here, which will be much more prevalent in future. So the likes of NVIDIA and AMD, they're grumbling about the slow development of things like GDDR. So GDDR6 was just announced the specifications for that, but they outlived the usefulness of GDDR5 already, and they start to use HBM. So AMD started with that, but you also can now find this kind of architecture on NVIDIA cards. And to some extent, you will also see this on CPUs if it becomes necessary. So what does this mean for the programming side? It means that we need even more NUMA levels. So before we go there, so let's look at the die architecture. So at the very beginning, so the second slide, which is or the third one, I showed the Skylake core architecture. So, but that's just one piece of the puzzle. So this is how a high-end Xeon Skylake processor at the block diagram level looks like nowadays. So these green blocks which you see there, this is what I showed before. These are the individual cores. Attached to that, you have these uncore parts, which consist of some communication units, there's the Snoop filters, which are cache handling, and the actual last level cache, which is local to each core. It's always done like that, so they are not separate by itself, again because of the yield method. So if you have a mistake somewhere, you just turn off a cluster of them or one of them and so on, and you can sell the chip with some fewer number of cores and so on. But in its full form, it looks currently something like that. So those who have been looking at CPU architectures for a long time will remember that initially we had them all, the few cores which we had connecting directly. Later on, until before Skylake actually had something called rings, where they were attached to one or two rings which were coupled on the chip, and Intel was very vague about which core was actually in which part of the rings, etc. They didn't want people to think about this for some reason, for a good reason actually, because it adds so much complexity and the differences were not as high because of the architecture. But now they actually introduced, oh, sorry. Oh. Okay. So now they introduced this mesh architecture. And with it comes the problem that they actually expose that not every core is the same. If you have cores on one end trying to communicate with cores on the other hand, there's a diameter of the network, which is different based on which core tries to connect to those, which means that certain levels of memory have certain distances. Larry showed this morning with this information which you can gather from the kernel. Guess what? It's getting more complicated. If the kernel selects to do so, we can have very, very fine-grained information about what's the distance from each core to each other core. And it will be different. So high-performance code will have to take this into account. And what I have not shown here is that they actually have some bigger boundaries in the middle. So the Skylake in a moment has two of these, I don't know what the actual core terminology is, some kind of blocks. So you have the left side and the right side, and crossing between the two sides is actually even more expensive. So, and you can expect this to be ever more complex in future. So I think for the time being at least, we're going to stick with, or we're going to see and have to live with these kind of mesh architectures. They introduced this just now because everything else with the number of cores which we have now is simply unattainable. So it's not really workable anymore. But this means that we have huge problems programming this thing efficiently. So, and now let's think about two of these in the system. So, and here I have just listed a couple, not even all of them, all the NUMA levels which we have to worry about. So we have now, as always, level 1, level 2 cache, which are on the core itself. Very simple. Then we have the level the level 2 cache, or level 1, level 2. So then we have the last level cache, the local last level cache, because as you can see, the last level cache is distributed amongst all the different cores. So after that, we have caches, the last level caches, on the neighboring cores, on the direct neighboring cores. But there are cores with varying differences of distance. So this is not just one number, these are a couple of numbers. So, and then we have local DRAM. So it's the memory which is attached to the local CPU, but this itself has different access speed than the local NVRAM. And I haven't even talked about the second socket yet, because all of that exists then for the second socket, and if a third socket is not directly attached, as Larry also mentioned this morning, to the first CPU, it multiplies and multiplies again. So out of the 3 or 4 levels of NUMA which we had, and the kernel currently only cares about 1, we might actually see 40, 60 different levels which a well-performing program will have to worry about. If you don't call this capitulation of the CPU designers, then what? So the other thing, which is, and I'm going back to the architecture of the core, of the CPU core. So I've harped on the memory subsystem right now. The other part, which is problematic, especially on the CISC processors like x86, is instruction decoding. So you might not realize this kind of thing. that part up there, which is where it reads the bytes which make up the individual instruction and tries to decode them and decide what actually they mean and how to execute them, etc., that's a major bottleneck. It's amazing what especially Intel and AMD have been able to do in their current incarnation of hardware to actually speed this up. So x86 instruction set is notorious for not having a uniform instruction format. It's not all nice 32 bits with fields which mean something specific. No, it's variable length. From 1 byte to up to 16 bytes in size is one single instruction. And we don't know ahead of time what it means. We have to read the first byte, based on that perhaps the second, the third, etc., etc. And to make this fast, you have to do all these kind of things in parallel. You cannot only check for 1 byte instruction and then do the 2 byte. That takes too long. All of these things has to happen in parallel. And basically, this means that the instruction decoding engine nowadays on chips is a major part of A, the latency, and also B, the energy use. So we cannot really work efficiently with an instruction set like that. The only way out of this, and think back, I mentioned at the very beginning that so if we are talking about performance, high performance, we care about these kind of things, we really care about high performance computing. We can only deal with that, the problem of the decoders, if we avoid issuing many instructions, if we have instructions which do a lot of work at the same time without requiring a next instruction to be read. So this is, of course, also nothing new. This is something which has existed for quite some time. So Intel AMD introduced this with something called MMX, very early on, I think 2000 or something like that, around this time. Which were the assembly instructions and so on. So we had these kind of things there for a long time. But they have simply increased the vector size which is used for that. So instead of having 2 operations done, nowadays we are up to 512-bit wide vectors, which are the registers which are holding this piece of information, and which you can operate them in one single operation. In theory, some of the operations are using byte-wise information, some 2 byte-wise, etc., etc. So these kind of things, there is a lot of energy and effort spent into that. So it even goes to the point that with the latest incarnations, where we have these 512-bit vectors, if you would run really nicely tuned code, which can take advantage of the 512-bit vectors, the CPU will actually, and now comes the kicker, be slower. Because the energy use of the CPU is so high that it overheats and it has to throttle. It's unbelievable what these people get away with, so to some extent. It's ludicrous. But yeah, if you buy the machine and use the AVX 512 extensions, it might actually be slower than would use the AVX 256. It's a problem. So finding out how to correctly write your code will become even more of a challenge. And it might not even be that the same function will work in each context. So for instance, many of the math code and so on is using by a library called BLAS, which is the basic linear algebra library, which everyone is using, including all the machine learning code. And it might have to have situation-dependent implementations of the individual functions. Oh yeah, if your CPU is high, temperature is high, you have to use this code, otherwise this one. Okay, so in my opinion, the CPUs we are seeing today are really good for lazy programmers and no one else. Ideally, we want to have something where we have more control over that. We don't get this. So I mentioned HPC, so especially in the context of the algorithms in machine learning and optimization and so on, which are important nowadays. Let me just briefly say what kind of operations we're talking about. So we have dense matrix multiplications, or operations, additions, vector-wise additions, vector-wise multiplications, etc., these kind of things. Dense means simply that the individual elements are arranged in memory consecutively. But much more important, actually, are sparse matrices. This is where they have huge number of zeros in there and a couple of non-zero values. Why is this important? Because if you want to write algorithms based on graphs, you translate them into sparse matrices. So everyone who's using Google search or anything like that is using sparse matrices. So the Google search algorithm is based on eigenvectors of these sparse matrices. And getting good performance out of that is the critical thing. Well, guess what? It's not that easy. The other thing is in HPC, what's important is finite element methods, mostly used for things like solving differential equations. So it's just an example here on the bottom. Anyone knows? Navier-Stokes fluid equation. It's a fluid equation. It just describes how fluids are moving. And so how these are done is in 2 or 3 or even higher dimensions, you're looking at the neighborhood, taking all the differences of the values into account and then updating the local value, etc., and do this. So it's an in-memory update of the entire data set and so on. And that's the most important equation when it comes to all kinds of simulations, or not the equation, so this kind of method, so finite elements. So we have to actually support for that. And all of these methods have in common, as we already briefly mentioned and so on, that we have the same operation to be operated on multiple pieces of data, all the same operations over and over again. And so the decoding part is a huge problem when it comes to this. But we also have, for a long time, known much better solutions for that. So anyone ever worked with Crays, Cray1, Cray XMP, things like that? So in those machines, we were able to actually program them, vectorization, the right way. We just told the machine, here's a vector, it has this size, do. Instead of with SIMD we have to say, oh, let me see how long the vector is, and then let me see how large my short vector is. I have to do the division, do that many repetition of this loop, then do some cleanup work. Maybe do some cleanup work at the beginning as well. There's a large amount of overhead associated with this, but also more importantly, if you want your code you run on different generations of the same CPU, of the CPU architecture, you need to have different code paths. And if some manufacturer wants to actually optimize his or her implementation specifically and adds more arithmetic units to it, the code looks different. So the nice thing is that we actually have different things. I will talk about this more in a bit, but the same problem actually exists also on GPUs. So they are not necessarily the good thing which they promise, well, they're promised by the manufacturers to be. They are better at these kind of jobs because there are many, many more registers, there are threads, there are vector sizes which are variable. So you can have up to 2048 threads and 2048 operations with a single instruction controlled. But there's a lot of problematic pieces around the GPUs by itself as well. So first of all, you see here, this is one of what AMD calls a streaming multiprocessor. That's one tiny little piece of it. So the green parts are the cores. Each can execute one single instruction, so one single operation, so like addition and so on a 32-bit, or if they use the yellow pieces, they're on a 64-bit value. So but let's talk about 32-bit. And many of those are making up a cluster, and many of those are actually making up the entire chip, which means to actually utilize this kind of thing efficiently, you would have to write a code which can efficiently take advantage of more than 120,000 threads. I don't know how many pieces of code you have written where you can do that. And you have another issue with the actual execution part. So as soon as you use vectorization, conditions become a problem. So here's a little bit of code, very simple one. It happens very often in this kind of form for filters or for finite elements and so on, where you have boundary conditions that have to be dealt with. You have different threads working on the same data set and so on at different indices. So, and usually you have some variable somewhere, an index variable, in this case I. And, well, what happens if you execute this code? Well, all of the instruction for all the threads is exactly the same on a GPU. You have no possibility to do that, do anything else. So the code, the compiler actually has to generate is a sequential piece of code. And to solve the issue of a condition, what you actually have to do is turn on or turn off the individual threads. So if you have many if cases, so think about a case, a switch statement or something like that in C or C++, you will reduce the efficiency of your code tremendously, because most of the time, most of the threads actually don't do any work. They are turned off. And even if the processor has to turn off all of the threads for a specific instruction because all of them are fulfilling the same condition, they still has to go one after the other through all the instructions before it can turn them on again. So GPUs work really well for certain specific cases of code which are selected for this. So it's actually the point that right away that the problem was selected based on the architecture available, not the other way around. Yeah.
It's not more an issue on NVIDIA Volta. They have separate program counter structure.
Well, so the comment was it's not correct for NVIDIA Volta. No, so you have a fine grained, you have a granularity and so on. But to make progress among, so if you select your group to be large, all of them have to execute this. Otherwise, you have multiple of these warps acting independently and so on. And then you only have 32 threads or something like this, but you still have to turn them off. So the 2048 is not the only number you can tweak, but this also shows, in addition to what I said, there's more complexity even in programming those, because you have to select how you do this. And if you select multiple warps, different warps, you have to synchronize at the end of the critical, at the parallel region, which adds another overhead, as opposed to if you use a single vector. So there's huge amounts of variability when it comes to all of this. Okay. So the common problems I already mentioned there. So in general, we have code which looks completely different depending on the architecture and the sizes of the vectors and how we had the Q&A at the same time. So it's over here. So basically, so I just want to have one additional thing here. Is I mentioned the cray-style vectorization which existed and so on for a long time ago, but this is actually revived. There's an architecture called RISC-V, which people might have known. So it comes from effort based on Stanford and so on. They actually are looking into reviving the whole thing, where they will be using cray-style vectorization again. So, and for that, this is the code how you would add vectors of 32-bit values. And if you want to change the same code to do additions of 16-bit values, that would be the change. Almost nothing. That's the right way of doing this, not the way we are doing this with Cindy. So I don't have the time to talk about the accelerators. Basically, we have all kinds of accelerators which are going to do attaching to the system. They can be external, they can be in another socket, they can be on the package by themselves, they can be in the core, or most interestingly, they can be in memory. That's going to be specifically, this part is going to be the only way how we can actually achieve exascale computing. There we don't have to actually transfer the memory content to the CPU and back, which is this 40 picojoule, which I meant at the beginning, because it all stays on the memory module. But this requires us to actually design completely different software architectures. We have to do away with the thinking of the sequential execution. We actually have to think about it all in what we used at the very early days of computing, in batch jobs, in mini batches. Say, this is the operation I want to be performed, tell me when it's done. And how it is done depends on the architecture. And fortunately, the C++ actually standard has very much good support for that. All right, so I don't have the time here to take any questions, so I will stay outside a little bit if you have any questions for that. Otherwise, thanks for listening.
Thank you for the nice talk. Right, have to wait for the next, who the next volunteer is.
Exactly.
Are you just doing half-hour break?
Yeah.
Same as me?
No, actually,
You're doing longer.
I'm doing longer, but I will stay here anyway.
Oh, yeah. So I'm just taking off now.
I'm just going to come back to watch the